Hello again, everyone. In this video, we're going to continue our preparation for some of the properties of integration by looking now at upper and lower sums and how they're going to change whether you look at, say, the upper sum of a sum of functions or maybe the scalar multiple of a function. So let's see here. Well, I'm not going to name the theorem. It's basically going to be the same as this title here, right? So there you go. Upper and lower sums for function sums and multiples. So we're going to start with two functions, f and g, with, say, the domain a, b. And of course, because we want to eventually compute upper and lower sums, we're going to assume that these are bounded functions. Let's see. C is going to be some real number. And then I'm going to take a partition. Since we're talking about upper sums, I need to have a partition in play. So this will be, let's say, some n partition of the interval AB, and I'll use my typical notation denoting the kth interval in the partition by I sub k. So I sub k will go from wk minus 1 to wk. Okay, and of course this is for k equals 1 to n. Fine. As before, that is in the previous video, I'm going to write down each of the statements and I'll just prove them one at a time, although actually I'm only going to prove half of them because I'm going to leave the other half as exercises. So the first statement is that if I compute the upper sum for f plus g evaluated on this partition W, so this will be the f plus g upper sum of W, then this is going to be less than or equal to the f upper sum of W plus the g upper sum of W. And this actually causes some confusion. A lot of students write that these are equal to each other. They're generally not going to be. And in the argument as to why this inequality is true, you'll see why we know we're only going to get an inequality, not an equality. All right, so let's do the proof here. This is basically going to come down to our sup and inf omnibus theorem that we proved in our previous video. So let me start from the f plus g upper sum of W, and I'll just write down the definition. So this is going to be the sum, k goes from 1 to n, of the supremum, and now I'm going to evaluate f plus g on the interval I sub k. Okay, so I'm taking the supremum of this set. F plus g evaluated on the interval gives me it's the range of f plus g, and I can compute the supremum. And then I'll multiply by the length of this interval ik. That's not really going to come into play very much here. Now, in the supremum and infimum omnibus theorem, right near the bottom, we had some properties. Yes, here we go. What happens when I take the supremum of a sum of functions? And the answer is, well, I don't get the sum of the suprema. I get less than or equal to the sum of the suprema. So I come back here, and I can replace this supremum with the supremum of f plus the supremum of g on this interval ik. However, there's a cost. This becomes less than or equal. And so now I'll have the supremum of f of ik plus the supremum of g of ik. And I multiply all that by L of ik. And remember, the reason why when I split I get this less than or equal is I'm now computing f and g on the entire range independent, or the entire domain ik independently of each other. Whereas up here, they both had to have the same input. So if I chose some a in ik, I'm looking at f of a plus g of a. Whereas down here, I can take some x in ik and some y in ik, look at f of x and g of y. That gives me more opportunities to get bigger stuff. So that's why I get a less than or equal to. Okay, and now I finish it off by just playing a little algebra trick, right? So I'll distribute this L of ik in and then split the sum. So I'll get the sup f of ik times L of ik, and I split the sum, and now I'll have the sup of G of ik times L of ik. And this first bit, this is exactly equal to the F upper sum of W, and the second bit is the G upper sum of W. Okay, so that's the proof for number one. Okay, number two is going to be essentially the same thing, but for lower sums. Based on our previous video, it won't surprise you a ton, I hope, that the inequality changes direction. And that's because the lower sum is going to be in terms of the infimum. And for the infimum, when we do this infimum of f plus g, back in our omnibus lemma, right, or theorem, we had that the infimum of f plus g was greater than or equal to the sum of the infima. So this will be having the lower sum of f plus g will be greater than or equal to the sum of the f lower sum of w and the g lower sum of w. So I leave this one as an exercise. Okay, number three. Well, what if instead of adding the two functions, I'm going to multiply the function f by a scalar? And I still compute the upper sum on w. So as we saw again in the omnibus theorem, let's run it back for a moment. When we tried to compute suprema of a constant times a set, the answer we got depended on whether the constant was positive or negative. If it was positive or non-negative, really, we would get a constant times the supremum of the set. But if it was negative, we'd get that same constant, but now times the infimum of the set. So we shouldn't be surprised that we're going to get two cases here. And again, it'll depend on whether C is negative or non-negative. So if C is negative, I'm going to flip things around. If C is positive, well, okay, I get just C times the upper sum. So that's when C is non-negative. And if C is negative, I'm going to get C times the lower sum. So this tells us what to do if we're trying to compute an upper sum of a scalar times a function. And, well, okay, how about I'll do a proof of this one. So, oops, trying to switch colors here. There we go. All right, so again, we're using the omnibus theorem. I'm going to start from the definition. I write, okay, this will be a sum. K goes from 1 to n. I have the supremum of C times F evaluated on IK multiplied by the length of IK. Okay, now this CF evaluated on IK, that's the same thing as C times F of IK. All right, I'll just put a little dot there. Okay, so F of IK is the range of F on IK, and when the C is positive, I know I can just pull it outside the supremum. If the C is negative, then the supremum is going to turn into an infimum when I pull the C out. So this is actually going to have two cases. In the first case, where C is non-negative, I'll have a sum, but now I pull the C. In fact, I can pull the C all the way out of the sum as well, and I'll just have the supremum of F of IK times L of IK. So that's when C is greater than or equal to 0. If C is less than 0, when I pull the C out of the supremum, I end up with an infimum. But now you can see this top one is just C times the upper sum. So C times the upper sum. And in the bottom one, I have C times the lower sum. But for F now instead of C times F. Okay, so that's the proof. Of course, there's a fourth one, and that's what happens if I multiply the function and then look at the lower sum. And again, I'm not going to prove this. The proof is nearly identical. Just go back again to this sup and inf omnibus theorem. So if I take the lower sum for CF on W, this is going to equal, if C is non-negative, just C times the lower sum. And if C is negative, it comes out, but I get C times the upper F, the F upper sum of W. And there we go. All right. So probably we're going to do one more preparation video before we get into the integral properties. This is just to make it so that when we prove those integral properties, they are really clean proofs, very straightforward and fast. All right, we'll see you all next time.